All right, so believe we are live now. So let's recall quickly where we left off yesterday, which is the game of geography. And there were a couple of warm-up things that we looked at. First, we said, okay, let's play paths on a chessboard, where you start off on a chessboard making moves by marking squares that are currently unmarked, and you're only allowed to mark a square that is a neighbor to a square that has been marked in the previous round. And from here, we went to geography, where you basically rattle off names, following the rule that the letter with which the name that you speak begins is the same as the letter with which the name that was spoken in the previous round ends. So hopefully that makes sense. It's probably just easier to see the example on the slide than to follow what I said, but think of it as Antakshari with cities or whatever category of names you want to play with. Now, the graph abstraction of geography is fairly natural. We said that we have in this case, a simple and undirected graph. And essentially, you take turns to mark vertices. And once a vertex is marked, it's off the table. You can't mark it again. You cannot pick it up again. And in this book, they try to remind us of this by essentially deleting the vertices. But if you like, you can also just keep them in some sort of a marked state, knowing that those are inaccessible. And the idea is that once you have, so you can actually imagine this is like a graph laid out on a table and a token being placed on a vertex to begin with. And essentially, you can only move the token along the edges to vertices that are still available. So imagine that initially all the vertices are white and a token is placed somewhere. And once a token is moved out of a vertex, the vertex is colored black. So you can't enter a black vertex. You can only enter a white vertex. So that's the setting of undirected vertex geography. And one of the questions we asked in this context is, if you're playing an exhibition match, for how long can you make it last? He said, basically, the longest you can go is n rounds, which is to say that your token must visit every vertex of the graph. You cannot, of course, do more than this, because you can visit a vertex, or a token can be placed on a vertex only once, not more than once. So if you do have a game that goes all the way, then you have effectively traced a Hamiltonian path in the graph. So the games where you can max out this length are precisely the graphs that have a Hamiltonian path. Now, I'm not suggesting that playing along the Hamiltonian path is necessarily optimal play, but if, like I said, imagine you're doing an exhibition match, then you can use the Hamiltonian path to make the game stretch all the way, right? And now there are a couple of variations on this that I had mentioned in passing last time, which is to say that your graph could be oriented, the edges could have directions, which is more faithful to this original game, because notice that, for instance, you can go from Plymouth to Halifax, but you cannot come back from Halifax to Plymouth. So, but on the other hand, there are examples of words where you can go both ways. If you have a word that starts at some letter and ends at some other letter, and you have another word where it's kind of the opposite, then it's flexible. You can go from the first word to the second, or from the second word to the first. So having edges being directed essentially accounts for this more sort of general model of the game that we are coming from. And the other option is to also do, instead of vertex geography, you can also do edge geography, where instead of knocking out a vertex in every round, you are knocking out an edge, or you're picking an edge. So we'll come back to both of those in a moment. But about vertex geography, we basically said that we had a strategy that worked for paths on a chessboard, which involved imagining that the chessboard was tiled with dominoes in a manner that basically constituted a partition of the set of all squares into these 2x1 pieces. And remember, by a partition, I really mean that every square is covered exactly once by a domino. So the dominoes don't overlap and they don't leave any gaps, right? The question was, what's the analogous thing that we can do when it comes to a graph? So if you have a domino tiling, of the entire board, then the second player has a winning strategy because they can just keep coloring the uncolored portion of the domino on which the first player makes their move. And you can keep going in this fashion. And we said that in a graph, the natural way to generalize this idea of a domino covering is via what we call a matching. So this is a collection of disjoint edges. And we said that if you're starting off with a token on a vertex V and you have a graph G, then the first player has a win if and only if in the graph, every maximum matching saturates the vertex V. And remember, the word saturate simply refers to the fact that the vertex belongs to one of the edges in the matching, right? So in this picture that we have here to the left, the vertices here are the ones that are saturated by the matching, whereas the vertices down below here, those are the ones that are not saturated by the matching, right? And notice that if you have a token somewhere here and you have to make a move, then any valid move takes you right back to a saturated vertex, because you cannot have an edge that takes you to another unsaturated vertex, because if this edge was present in the graph, then this portion here would not be a maximum matching, because you could have added that edge and gotten a bigger matching, right? Okay, so all of this is mostly recap. Now let's actually try and prove this claim that we are making here. So let's do one direction first. Suppose every maximum matching saturates the vertex V. Here we want to say that the first player has a win. So the first player has to move the token out of V. Let's fix one maximum matching and let me call that M. So let's fix one. And because it saturates V, there's one edge in M that has V as one of its endpoints. And then there's a bunch of other edges. And potentially there are some unsaturated vertices as well. There may not be any unsaturated vertices in the sense that the maximum sized matching may actually be one that is perfect, which is the case when basically every vertex is saturated by this matching. So you may be in a situation where this collection of unsaturated vertices is actually the empty set, but there's no guarantee that it's the empty set. The maximum matchings in many graphs are not perfect. So that's something that we have to live with, right? So for example, if you just have a triangle, then the size of the maximum matching is 1, and no matter which edge you pick, you will always end up with one unsaturated vertex, right? Okay, so let's come back to the first player strategy. What does the first player do? Well, just imagine what you would do as on the chessboard game. Essentially, you're trying to always attack the partner tile in the domino covering. So here the edges are like the dominoes. So what the first player is going to do is they're going to move the token from V to the partner of V in the matching. Yeah, let's say this is what the first player is going to do. Now, the second player, notice that will necessarily end up playing on an edge that does not belong to the matching, right? So this is E that belongs to the matching, and that's the first player's move. Now, because you end up on a vertex, let me call this vertex W, which is already saturated in the matching, and you have already traveled the edge that saturates this vertex in the matching. Notice that all the other edges that are incident to W must not belong to the matching, because the matching by definition is a collection of edges that don't share an endpoint. So W is already taken, and you can't have another edge in the matching that also comes out of W. Now, of course, it's possible that W has no other edges incident on it, in which case the game is already over and the first player has an immediate win. So to keep things interesting, let's consider the case when W is not exhausted, that there is still an edge on W that's feasible for the other player to take. The other situation where the first player wins is if there are edges incident on W, but they all go to vertices that have been chosen in previous rounds. But again, like I said, I want to make a general argument here. So let's say that the second player has a bunch of choices going out of W. So these could lead to either unsaturated vertices or saturated ones in terms of what is the other endpoint of W. But the main point here is that the edge along which you travel is an edge that does not belong to the matching, right? So let's say that the second player moves along any one of these edges. Then notice that the first player essentially can respond by taking up the other. So if, for example, the second player comes from W to, let's call this vertex U. Sorry. Then the first player's response would essentially be to move to the other endpoint here, and they would manage to keep the game going by moving along the other edge of the matching, right? Now, this gives you a sequence of edges that alternate between belonging and not belonging to the matching. And in general, this is what is called an alternating path with respect to the matching M. Now, let me see if, sorry, I think my pencil here is disconnected from the screen. Just give me a second to fix that. Right. So as long as you're playing, as long as the first player is okay, hopefully this is visible. So as long as the first player is being brought back to a vertex of this kind, U, which is a saturated vertex, they can continue the game in this alternating fashion that we just described, right? So the first player sticks to their lane and they always play along a matching edge. And no matter where the second player takes them, right, what we will end up having is a situation where the first player has an opportunity to continue. However, what happens if you're in the other case where the second player's move takes you out to a unsaturated vertex, right? In this case, this can get a little tricky for the first player because, well, I mean, the next move will indeed bring you back to the matching because, like we argued a moment ago, you cannot have edges between two unsaturated vertices in the graph even, because then that would contradict our assumption that the purple edges here form a maximum matching. So you can't, so you can't have edges out here. So any move that the first player makes will bring them back to the matching. And of course, it's not even clear that, the first player is guaranteed a move. You might well be on an unsaturated vertex where you get stuck, right? And here, of course, in the first situation, when we were dealing with the vertex hue, that was not the case. Notice that you are not stuck if the second player brings you back to an saturated vertex, because essentially it's like what we said with the dominoes. We are maintaining that the edges of the matching are always unused. Like what you're maintaining as an invariant is that the second player never gets to play along the edge of a matching, because you are the one who calls first dibs on the matching edges. So you start by playing on a matching edge. The second player is forced to then pick an edge that's not in the matching. And then you again play along a matching edge. The second player is again forced to pick an edge that's not in the matching, and so on. So for as long as that's possible, things are great. But right now in this situation, we would be somewhat in trouble, because now we are breaking this invariant, because now every edge that's available back from an unsaturated vertex to a saturated one will be an edge that's outside of the matching. And then this breaks the pattern for the first player, right? So we want to argue that this sort of a situation is actually not possible. And let's see why that's the case. So let's say you're tagging along happily for some time. So the moves made by, I think, let me try and be consistent with the colors just to remind ourselves of what's happening. So the first player plays along a matching edge. Let's say that the second player responds by taking you to a saturated vertex. Then life is good. You play along the matching partner of the, you basically go to the matched partner of the saturated vertex. Now, the second player is forced to play along, again, a non-matching edge. Let's say they again take you to some saturated vertex, then you're again happy, you play to the matched partner of that saturated vertex. So in all of these cases, you know that these edges are available. However, let's say that at this point, the second player has some sort of a master stroke move, which takes you to a vertex that is unsaturated. So let's say this is an unsaturated vertex. Okay. And let's look at where all the other matching edges are from the purple matching, which we claimed was a maximum matching that saturated the vertex V, because this is where we started. This was our first move, getting out of V. And this is the, let's say, the rest of the maximum matching. And this vertex right here does not belong here. It's an unsaturated vertex, so it does not belong here, right? Okay, so in this case, what we are going to do is derive a contradiction to our assumption that every maximum matching saturates the vertex V, right? And the way we do that is by producing a maximum matching that does not saturate the vertex V. So what is the cardinality of a maximum matching just in this example? Well, the maximum matching happens to have 7 edges, because we are staring at this maximum matching here. From the alternating sequence, we have 3 edges in the maximum matching. And from the remaining, I've drawn 4 more. So every maximum matching in this graph has 7 edges, right? Now you can probably see where this is going. What I'm going to do is propose that we augment this part of the maximum matching using not the purple, but the green edges from this part of the graph. Right? So here is where the game has already been played. So I'd say let's pick the green edges. Notice that the green edges are all disjoint because they were kind of alternating here. So between them, there are no violations, and none of them will overlap with the remaining 4 edges of the purple matching, right? And that's kind of clear because all of these vertices here were anyway saturated by M, so they're not going to show up again here. And this fellow is anyway outside, so that's again not a problem, right? So essentially swap out the first 3 purple edges with the first 3 green edges coming from the gameplay, And what you have done is you have discovered maximum matching because you have replenished the matching with as many edges as you've removed. I removed 3 purple edges, but I also brought in 3 green edges. So the size of the new matching is the same as before and is therefore maximum because you started with the maximum matching. But notice that you managed to knock out V, which means that you've actually produced a maximum sized matching that does not saturate the vertex V. But this contradicts our assumption that every maximum matching saturates the vertex V. So effectively, moves of this kind will not be available to the second player because if such moves actually existed, then you can discover a contradiction to the structural assumption that you have made. So essentially, every move that the second player makes forces him or her to come back to a saturated vertex. And that just gives the first player a lot of breathing space to continue playing along the matching, right? So in some sense, the first player is never stuck, right? Okay, so that's the argument in one direction that if every maximum matching saturates V, then the first player has a winning strategy that basically involves playing along the matching. So you fix the matching and you just wait for the moves to be made by the other player, and they're guaranteed to bring you back into a saturated vertex whose matched partner has not yet been visited. And so you just go along the matching edges. And what we just argued is that the strategy will never fail. You'll always have room to make progress. So it's the other player who's going to get stuck eventually and lose the game. What if there exists a maximum matching that does not saturate the vertex V? And remember, V is special because that's where the token is at the start of the game. So if there exists a maximum matching that does not saturate the vertex V, well, then the tables have turned and you can essentially do a strategy stealing sort of an idea. So you have the vertex V, and now because again, this is a maximum matching, no matter what move the first player makes, they are going to land up inside the matching, right? Because if they're able to make a move that lands up outside the matching, then this edge can augment this matching, which will contradict our assumption that it is a maximum matching, right? So every move basically takes you into this fire pit, essentially. And now the second player has the same sort of a fate as the first player did in the previous argument. So the second player is now the player that can continue to play along the matching edge. And the first player will be again constrained, will remain constrained to move in here. And like I said, it's basically a tables turned kind of a scenario. And you can work through the same argument, but now on behalf of the second player, right? So if there is a maximum matching that does not saturate the vertex V, then that's the matching that the second player can basically hold on to guide their moves, right? And just to confirm your intuition here, suppose this edge was PQ. The red edge is the first player's move, and let's say that the second player moves along the edge PQ. And let's say hypothetically that the first player is somehow able to get out to an unsaturated vertex. The reason this cannot happen is because if you have, notice that this basically gives you, again, an alternating path. By an alternating path, I mean a path where the edges go between matching and non-matching edges. But in this case, the alternating path begins and ends at 2 unsaturated vertices, right? So we have V on the one hand, let's say this is some vertex U. But as is hopefully visible here, this contradicts the fact that the purple matching was a maximum sized matching, because you can basically knock out this edge here in the middle and replace it with these 2 edges. And now, in fact, you get a strictly bigger matching, right? And therefore, you contradict the assumption here that the purple matching that we started with was a maximum matching. And although I have shown this to you on just the first three moves, the same argument applies if this issue shows up later. So it's possible that you've played within the matching for a while, and at some point, the first player is able to get out of the saturated zone. If the first player is able to do that, then you can trace your way through the gameplay, and you'll basically end up with a situation which is exactly of the kind that we prescribed, which is that you have an alternating path between two unsaturated vertices. And that just does not happen if the base matching is a maximum matching. Okay. So just to recap, there are sort of two main ideas here. One was the fact that if you have this sort of an alternating path that starts at the vertex V and ends at an unsaturated vertex, then you have the same number of edges that are matched versus unmatched. And because you're ending at an unsaturated vertex, you can swap out all the matching edges for the unmatched ones to get a matching of the same size, but one that avoids V. So in this case, you contradict the assumption that every maximum matching saturates V, which is what we said was needed for the first player to have a win. So we are assuming that that's true and trying to argue a first player win. And that's what gets contradicted if the first player is stuck. Okay. All right. So on the other hand, we said that if it is not the case that every maximum matching saturates V, then there must be one, at least one that avoids V. And we said that that will form the backbone of the second player strategy. And here, if the second player ends up being in a bad situation, which is that they can't constrain the first player to be moving within the set of matched vertices with respect to this matching that exists, then the presumed gameplay where things are not working out for the second player can be used to extract a larger matching than the one that we started with. And that will contradict our assumption that the matching that we started with was a maximum matching, right? So the second player will always have a way to make progress. All right. So good. I think that's both sides of this argument. And at least for once, I'm reasonably convinced about both the aspects that we looked at. But if there's anything that did not make sense, then please do let me know one way or the other. I'll also try to share a link to some notes that I'm putting together about this, where we sort of go over both of these arguments in some detail. If you're following along with the book, then this is also 1.1.2. And they make pretty much the same case here with also the same terminology. So hopefully that should be easy to revise from. Now, I don't actually have a whole lot to say about the two other game variants, but let me just mention again what they were. So one is, of course, to look at edge geography, which is basically the same, except you're going, instead of picking vertices, you're trying to pick edges. So once you pick one edge, the next edge has to be one that you can sort of continue from the edge that you played on. So if you're coming from U to V, then your next move must be along the edge that has not yet been chosen, that is going out of V, right? So again, the question that they sort of consider here is, what is the longest game that can be played? Just like we did with undirected vertex geography, and with vertex geography, we related longest gameplays to Hamiltonian paths, which are paths that visit every vertex exactly once. But notice that here we are not visiting vertices, but we're visiting edges, which means that it's possible that the gameplay takes us to the same vertex multiple times. That's totally allowed. So your games could continue in this fashion. So for instance, this is a move that brings you back to a vertex that in some sense you have encountered before. And that's fair play, because what you're not allowed to do here is pick an edge that has been picked before. But if an edge is not been picked, if it happens to share an endpoint with another edge that was picked before, that is not a problem. Okay, so essentially you are kind of walking around the graph, and in fact, such a sequence of edges where the consecutive edges basically share an endpoint. In fact, what I want to say is, to be a little more precise, is that you have a sequence of edges, E1, E2, and so on, where you can order the vertices in this fashion. So let me say this is U1, V1, this is U2, V2. Okay, so what I want is that V1 is the same as U2, V2 is the same as U3, and so on and so forth. That's what it means for this to be a walk. And what I was trying to emphasize earlier is that now the UIs and the VIs don't have to all be necessarily distinct. So you could be potentially revisiting vertices as you go along. Unlike Hamiltonian paths, Euler paths of this sort, so I've already said Euler paths without defining what they are. So Euler walk is sort of an analog of a Hamiltonian path in the edge world. So it's basically such a sequence. So it's a walk which visits every edge exactly once, as opposed to every vertex. And just like we said that for vertex geography, the longest that a gameplay can go is n rounds, because you cannot visit a vertex more than once. In edge geography, the longest that a gameplay can go is m rounds, where m is the number of edges, for exactly the same reason, that you cannot visit an edge more than once. But if you think about walks that visit every edge exactly once, so you're thinking about those games where you can really stretch it all the way and play a really good exhibition game, then, well, what are these graphs where you can walk around the graph visiting every edge exactly once? These turn out to be graphs that have a very nice characterization, and such walks which visit every edge exactly once are called Euler walks or Euler tours. So that's something to sort of look up if you like, because there's a lot of nice things that you can say about these things. So I guess technically our Euler tour is typically a walk that ends with the same vertex that it started with. So in particular, VK would be the same as U1. So you come back to where you started, whereas an Euler walk would simply be one that visits every edge exactly once without any obligation to come back to where you started. So whether you have a walk or a closed walk or a tour, you will still be able to take the game all the way. You don't necessarily have to come back to where you started. And it turns out that the graphs where such walks exist are graphs where almost every vertex has even degrees. So what you want is vertices to have an even number of edges incident on them. You're allowed to basically exactly two. I mean, if there must be an exception, there must be exactly two, because the vertex where you start and end, if those happen to be distinct, then those two are exempted from having an even number of edges incident on them. Those can have an odd number. Those, well, either two vertices, either exactly two vertices have an odd number of edges incident to them, or all vertices have even degree. These are the two situations where you can come up with Euler walks. And although I won't give you a proof here because we don't have enough time for that, let me just give you the intuition. So if you do have an Euler walk, imagine somebody going along that Euler walk, but imagine the walk from the perspective of a single vertex. So let's say your friend is walking around along an Euler walk, and you happen to be sitting at one of the vertices. And what's going to happen is that every so often, your friend will enter this vertex and leave the vertex, right? But every time they do that, they must be doing it along a different entry and exit point, because you're not allowed to repeat edges, right? So because your friend is going to enter as many times as they exit, if you are sitting on a vertex that's in the middle of the walk, it's not one of the extreme endpoints, you know that you can basically tally up the number of entries with the number of exits, which means that the total number of edges that are incident to this vertex must be even. So if the number of entries is equal to the number of exits and they're all distinct, each entry corresponds to a different edge, each exit corresponds to a different edge. So let's say the number of entries is equal to the number of exits is equal to x, then the degree of this vertex must be 2x. The only exceptions are if you're sitting at the starting or the ending point and they happen to be distinct, then, well, there is basically either you can think of it as the first exit or the last entry. Those are special. Other than that, again, there is this come and go kind of argument, right? So if you have an Euler tour or an Euler walk, then you can see that the natural degree conditions hold. What is also interesting is that if the degree conditions hold, then you can actually come up with Euler walk or Euler tour. So that's a different argument. It's not encompassed by what I just said. Because, well, one way to say it intuitively is that, okay, why don't you just take a maximal walk, just keep going, right? And hopefully you will end up with Euler tour. But this just keep going argument by itself, is really not enough because, for instance, well, here is a graph which is, well, it has exactly 2 degree 3 vertices, everything else is even. So, so of course you should be able to start here and come back and visit every edge exactly once. So I go here, 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 and here. So that's actually possible. So you can start here and end here. But if the argument is just, well, start somewhere and keep going until you get stuck, then you might end up, for example, starting here and doing that and basically getting stuck without having completed an Euler tour, right? So that argument by itself is not enough, but you can augment this argument by saying, well, okay, so suppose you started somewhere, you went on and on till you got stuck. And now at this point, suppose you have not covered every edge, then, let's basically do a restart from something that you have not visited and do the same. Basically do the same, go on till you get stuck. And it turns out that, with these restarts, what you're going to get is a bunch of fragments. And those fragments can be nicely stitched together to form an Euler walk or Euler tour, as the case may be, depending on what kind of graph you're working on. So that actually is implicitly even an algorithm for constructing an Euler walk or Euler tour. And so what I've given you here is like a few pieces of intuition for why all of this works out. I don't think these are, sort of watertight descriptions. So you should definitely go back and work through the details if you find all of this curious. And Euler walks and tours do have some very nice applications beyond edge geography. So it's a great rabbit hole to go down if, you find the concept interesting. The final comment I will make is for directed geography, and I'll just take 1 more minute here. I realize I'm over time, but directed geography is basically the same as here, except that the edges have orientations. And like I said, we allow orientations to be both ways. This is something that truly captures the original game of geography. But it actually ends up capturing a lot more because, basically you can think of every game tree as an instance of directed geography. So you could be playing essentially any game, right? And in particular, any impartial game, which is to say that, both players have the same set of moves at hand at every step. And in previous classes, we've seen, in previous meetings, we've seen how you can associate a game tree with any impartial game. Now, the game tree is really just a directed graph. Every node corresponds to a state of the game, and the directed edges basically tell you what states are accessible from the current one. And so really, if you think about playing any game whatsoever, you can imagine that you're essentially sliding a token along the game tree. And so if you know how to solve directed vertex geography, you can basically apply that to basically any game that you like. So that's, well, I mean, that's an interesting feature of the directed version of the game. It's clearly very it's a very abstract, very powerful sort of a model, encompasses not only the geography game as we saw it earlier, in terms of these names and so on, but also pretty much encapsulates gameplay for any impartial game. And again, you could ask the same question here about, how long can these games go? And, again, the upper bound on the length of a game is going to be n, because here again, you are sliding a token along vertices. You're picking vertices with the same constraint of not being allowed to pick any vertex more than once. So the longest a game can go is n. And once again, just like in undirected vertex geography, you can push it all the way only if you have this time a directed Hamiltonian cycle or a directed Hamiltonian path. Okay, so I won't really say much more about this. I think this is also where the book chooses to pretty much stop as far as geography is concerned. You can, of course, find out more about Hamiltonian paths, Euler walks, Euler tours, and directed Hamiltonian paths. These are all the sort of graph theory concepts that are very naturally associated with these games. And you could find out more about algorithms to find these substructures. The Hamiltonian side of things tends to be very intractable, but the Euler walks have these really nice, efficient characterizations. And I'm definitely encouraging of looking at both. They're both interesting and contrasting notions on their own right. But this is kind of where we will also conclude our discussions of geography. And from tomorrow, we are going to get started with, I think, chapter 2, which is partisan games, where the main difference from what we've been doing so far is asymmetry in the choices that the two players have. So think of something like chess, for example. On the set of moves available to the players are not the same, depending on whether you're playing white or black from a given position. So if I just give you, I take a snapshot of a chessboard from mid-game. If you were playing black and it was your turn, the set of moves that are valid for you is different from if you were white and it happened to be your turn. So that's what we mean by the game not being symmetric, being partisan. And that's not been the case for any of the games we have discussed so far. If I give you a snapshot of, say, a NIM game, then it doesn't matter whether you're the first player or the second player of the original game. If you're faced with this situation, both players will have the same set of moves at hand. So this is going to be a bit of a departure, and we are going to, as usual, look at a few examples of partisan games, ask all our usual questions. Who's going to win? What's the game tree looking like? What are the numbers associated with the states and so on? And that's where we will continue from tomorrow. And my apologies for starting a bit late and going over time, a bit of a double whammy, but we will stop here and continue this discussion tomorrow.